você acha que podemos começar? Boa tarde, pessoal, tudo bem? A palestra hoje é em inglês, então eu vou falar em inglês para apresentar o nosso palestrante, tá? Good afternoon, everyone. Thank you all for joining us. Today we have the pleasure of receiving Professor Hazem with us. He's from the University of Halmstad in Sweden, I'm not sure, Sweden. And he's going to present his lecture about 5G processing. And Professor Edson is going to present him in a few seconds. So thank you all once again for joining us, and have a nice lecture. Thank you once again, Professor, for joining us.
Thank you. Thank you, Matheus, for the introduction. I will talk very briefly about how Hazem came here. So we have a collaboration with Halmstad University, with funding from Linus Palme program. It's a program from the Swedish, from the Swedish government, and
I'm just going to my presentation here. Maybe it'll help. Just put it on full screen.
no, doesn't work
now.
Let's try the pointer just to check if there is battery. Just the last button.
Yes,
it's working.
So this is a cooperation that we have with Halmstad University, founded by this Linus Palme program, which supports the exchange of professors and students. So now Professor Hazem and Professor Wagner is in this part of the exchange, and we are receiving them. So I will give the floor to Professor Hazem so that he can start. We have to switch the presentation. No.
Thank you very much.
Here we go.
Thank you very much. Good afternoon, everybody. So I am Hazem. I'm an assistant professor at Halmstad University as a department of computing electronics for real-time and embedded systems and the School of Information Technology. From the name of the department, you can infer the type of research that we are doing at the department. We are concerned by computing devices and embedded systems, especially in the real-time ones. So we have several, I think, researches going on in the department. Some related to healthcare, which is, I think, managed by Professor Wagner at Halmstad University. Some related to design of embedded systems and parallel computing and hardware acceleration, which I'm concerned with. And part of this presentation will be focusing on that. Some related to like cybersecurity and how to secure like different systems in terms of software or hardware, and some related to communication. So today I will present one of the recent projects that we is running at Halmstad University related to the future generation of wireless communication. This project is an elite project. You can see here the link elite. This is a consortium in Sweden that collects or gathers several universities. Okay. Halmstad, Lund University, Linköping, Blekinge, I think so. I missed any other. So this group of universities, they have like try every time to come up with new ideas and try to tackle some top research topics and to lead the research in Sweden in these fields. So this is one of the research projects that has been started like last year in Halmstad, accompanied with other universities in Sweden as well.
Yeah, maybe we'll have to use a keyboard.
Okay.
you want me to introduce him for you? Or you can just use this.
So, our presentation outline, we have the motivation for this project, the reason why we started this project, and then we'll discuss the research challenges or the research questions that we'd like to address, and after that we discuss the proposed approach to tackle these research questions, an overview of the system model, the proposed one that we are trying to implement. It might change at the end of the research project to add something or change the design. And the research activities that has been done so far or previously that helps in achieving or like that helps the progress of that project as well. Okay. So the motivation, like, so now you can hear like there's a lot of advancement in wireless communication, and there's always like a need for high data rates. So like if you remember, like we had the 4G networks, now we have the 5G, and now like the research is going to think about the future ones. We don't know how they will call it. Is it 5G plus or 6G? That's why the title of the project saying like beyond 5G. So because we are not sure about the naming itself. Okay. So due to that, both academia and the industry are actively looking into beyond 5G systems and trying to identify what are the key service requirements and technologies that should be included in the future cellular communication networks. So famous like candidates for of technologies that will be included in the future wireless communication networks is large intelligence services, cell-free massive MIMOs, and millimeter wave terahertz communications. Another thing, like to include such kind of thing, you'll see, like when we'll discuss in the next slides, we'll give some kind of a brief overview in each of these technologies. So like to achieve or like to include all such kind of technologies, we have to opt to a different architecture, more distributed and cooperative architecture. So to include different systems and try to create some kind of an orchestration or synchronization between them. So this is one of the challenges that we'd like to address as well. So the first technology that we'll give an overview on is the millimeter wave terahertz communication. So it's an advanced wireless communication technology that operates in higher frequency bands. So like for the millimeter wave, the frequency band that we are targeting is from 30 gigahertz to 300 gigahertz. And for the terahertz, from 300 gigahertz to 3 terahertz. And the aim or the goal behind using these bands is to achieve much more higher like data rates because we have larger bandwidths at such kind of operating frequency. So you will have higher data rates, larger bandwidths, and you can adopt like higher capacity of communication as well and devices. So another benefit is like millimeter wave from its name, it has short wavelengths communication, and this will lead to more focused and directional communication. Now, like it's not about like to just have a coverage. You would like sometimes in some of the cases to direct your communication to a certain user. So if you see like at some certain area, geographical area, you have a lot of traffic. So maybe you'd like to direct your network to serve that area. Okay. This will help to have more to efficiently use the resources and as well will save the energy for the system as well. The terahertz as well works on shorter wavelengths as well, same than the millimeter wave, and they are suitable for short-range communication and as well even faster. So if you like to achieve like higher data rates at the short range or line of sight, the communication system can switch to terahertz communication. So these are very clear benefits that we'd like always to have in new wireless communication systems. But the problem here is that both of them are working at a very high frequency range, and this means that they are susceptible to attenuation. So when you have higher frequencies, like we cannot go through like obstacles like walls and concrete and metal and so on. So, and you can notice that at your home if you have like the Wi-Fi, newer Wi-Fi routers. If you operate on 5 gigahertz, you'll see like the coverage at your apartment will be even like smaller due to like the attenuation that happens through the wall and so on. Okay. And the other problem is the complexity of the design. So you like now to have multiple antennas to work at different operating frequencies and to be distributed in a larger geographical area. The second technology is a self-read massive MIMO. So the massive MIMO technology is already used in current wireless communication networks. It's a set of like antennas that are grouped at some certain location to achieve like larger coverage and to deal with multiple users. But the design at the current networks is like cellular design. So you have a group of antennas, hundreds of antennas, let's say, and you have a base station that controls them. Okay? So each base station processes the information coming from these massive MIMOs and deal with the users. So, but in the future, beyond 5G, we are looking for a distributed architecture, as you can see in the image. So you have one backbone in the area, and then you have subsystems. Each subsystem has a set of antennas, and you have some kind of sub-processing under them, and after that you can send the important information to the base station. This helps to become more energy efficient as well, helps in covering larger geographical areas. Because in that case, you are just covering in each base station, you're covering smaller. Okay. So this is a new design that many researchers are working on, but it faces as well several problems. And the main problem is the synchronization problem, like along with the complexity. Synchronization, because like if you are dealing with communication, so the heart of communication is the carrier frequency. So you have some kind of a main oscillator at each station. And if these oscillators are not tuned to a very precise value, so the difference between the clock frequencies is very huge, or the error is very huge, you will not be able to process the information and synchronize the communication on these antennas. So the synchronization problem becomes very relevant here. In the previous designs, so you have the base station, so you don't have this kind of synchronization problem at all, because the distances between the antennas and the base station is relatively short. But in the distributed design, it's very long, and there could be some kind of shifts in the clock signal and so on. Okay. Another key technology is the large intelligent services. So these are services like we are in the meant to be like interactive with the users. So like in the beyond 5G, we expecting to have to dedicate some certain services, walls or ceilings or even rooms to be smart rooms where you can interact with them, can sense your location and your position in the area, and then can interact you by targeting you, for example, by some certain ads that's coming to specifically to you, other than the different users. So this is a block diagram of an actual test bed in Lund University that we are working with. It's called LISA. So as you can see, set of antennas here on the walls, covering the 4 walls. And we have some different robots and objects are moving here. And we are verifying the location using the cameras as a reference to know the location and try to test different avenues to know if we can infer the position based on the communication that happens between the antennas. And we verify that using the cameras system. Okay. So one of the difficulties in such kind of technology is we have to detect or to accurately, precisely know the position. In smaller rooms in a closed environment like this, maybe it's a bit easier because the amount of interference is very low. But if you are talking about an open area, you will have more interference, so have to eliminate the errors generated from the dynamic environments as well. Okay. So these three technologies, we are trying to address them in this research project and to solve the problems that arise from them. So based on that, we identified our research challenges and questions. Okay. So you see that the first research question that we are trying to address is more about the distributed design. How to come up with a distributed design that can handle the massive amount of data generated from such kind of system to deliver to, this amount of data to the users or to receive them from data. And how large such kind of design will cover in geography. The second research question is how to deal with imperfections and the errors generated from distributed design and synchronization problem, as you can see, to support higher data rates and low latencies. And lastly, is more about the hardware requirements for such kind of system. How to design a system that can manage the resources efficiently and dedicate like computational resources dynamically in such kind of dynamic environment as well. And to achieve as well the higher data rates as well. Okay. So based on this challenge, we thought about like a system model. This is a block diagram of our system model. This is our backplane or the central base station. And here we have different set of massive MIMO antennas that have some kind of like analog, analog front end, and you have a digital front end, and you have some kind of processing, local processing for the signal, and so on. And these three research questions, as you can see, are converted into three projects between Lund University, Linköping, and Halmstad University. So Lund University is responsible for the system architecture, the distributed system architecture, how it will look like, the system requirements and topology, and so on, and how to distribute the processing among different blocks in the system. Linköping University, working on the communication part and how to handle the synchronization problem, and to how to create newer digital front ends to process the information, communicating. And Halmstad University, concerned by the hardware design requirements and finding task-specific processors or architecture that can match the computational requirements of such kind of systems, using data flow modeling and programming. Okay. So these three projects, we have 3 PhD students working on each project at each university. So some of the work that I will present in the coming slides are handled by my PhD student working there. So I mainly will focus on that part. I'll just give you an overview of the other parts, so I will not be able to present the research work done there, but I will present the research work done on that side. Okay. So the first research work that has been done was related to the application of the large intelligent services. So we said that the large intelligent services are like intelligent walls and surfaces that can sense the environment, process the information, and interact with the users. And our goal here is to enhance the positioning here of such kind of system. So there are many works has been done on find an act to improve the accuracy of positioning different users in the system, but still, like it didn't reach the required like accuracy needed. So still an open research question, and we have done some work based on a work done by a research group in Belgium, so who have done some kind of similar work, and they allowed us to use the data sets. So they have some kind of a test bed. We are lacking in that research project a test bed where we can put the massive MIMO antennas and try to create some kind of an real experiments to get real data and so on. But these guys already have a public data set which shows like different users moving in an isolated room with large intelligence services and showing like the readings that the antennas get from such kind of movement. So we use their work and we try to improve that. So before going in detail, I'd like to introduce some of the terms that you will see in that research work, like CSI, channel state information, CNN, I think some of you know, this convolutional neural networks using machine learning. URA, ULA, and DA, this is different antenna distribution schemes here. And the mean error. So CSI represents channel state information. It's like the information that's collected at the antennas from the communication that happens between the system and the users there. And this information, like represents when you send, for example, when an antenna sends an information to a car in a mobile phone, so it receives a response from the user itself. But since we have multiple antennas, you will receive a response from that antenna, and maybe you receive different responses from other antennas. So the signal will be scattered on different and received by multiple antennas, and you will get the same information. And based on that information that you receive on multiple antennas, you will identify like the how strong is the signal, and from that you can determine where your object is located in the system. So we're using such kind of features like the power decay with the distance to know how far it is from the antenna, the fading and scattering of how the signal has been scattered and reached multiple antennas. Okay. So the channel state information at the end, we have it as a matrix that have several numbers that represent such kind of information. CNN is a convolutional neural network. So it was proposed by the several research groups, especially the one in Belgium as well, to process or to work on the CSI information. And the reason for selecting the CNNs is because it was successful with image classification. There is a similarity between the images and the information represented in the CSI. So the image information, you can look to it as a matrix, same thing as the CSI information. And the important information in the image is sparse and scattered across the image. And CNN was very successful in finding these important features in the image. And due to that, we selected it to work with the CSI information because they are similar in nature. Okay. So this was the original CNN design that has been proposed by the research group in Belgium, as you can see. And they have reached an accuracy in the position up to 55 millimeter. Okay. So we had as well in our experiments 3 different antenna distribution. So we have the uniform rectangular array. So our antenna is distributed on both sides here of the room, or the linear one only on one side. So you can think about that as a wall, an intelligent wall here. And the distributed array as if like you have a room surrounding the area. So the idea from like having different distribution to see the efficiency of each distribution locating the objects, so we can study that as well. It's better to have it like this, and if it will be suitable for different environments as well. It's noisy environment or non-noisy environment. But in that work, we are not studying, like we are not experimenting with different environments. All the data that we had was in a closed lab room, so we don't have this kind of like interferences and so on, okay, from external sources. So this is here we have 8 antennas, but I think the experiment that we done experiment up to 64 antennas. Okay. the mean error, and this is a very important key factor that we use in evaluation. So we try to find the mean error and try to minimize it, because this will help us to have more accurate results in positioning. And you can see these are output of different simulations that we have done. And this is one of the best simulations that we reached so far. So you can see the blue lines is the actual position, and the orange one represents the predicted one from processing the information. Okay. So the proposed approach. So we have we took the original architecture, the CNN architecture, and we tried to change it to find a different one that can be more efficient and give us better accuracy. So to do that, we have selected 1000 architecture from CNN with this kind of configuration, and we trained it several times with the minimum number of epochs. And after the training, we picked up the best 3 out of them. Okay. So the configuration of the best 3 CNN architectures are found in the paper, so you can go and check them. But we picked up the best 3. So, but in general, we have changed the number of convolutional layers and the fully connected layers, and we have removed the dropout layer here. Original one. We go back here. So this is the dropout layer. We have removed that and we replaced it by batch normalization layers. The reason for that, the batch normalization layers have a higher learning rate compared to the dropout. So that's why we have done that. So the new architecture, we have CNNs, as you said, and in general, this is how they look like, the architecture. This is a common thing between them. It's not the details, because the fully connected layers and as well the CNN layers are different in each architecture. But this is the block diagram in general of the architecture. And after running the experiments, using the data set that we have, so you can see here, for the uniform rectangular array, the mean error, we reached it up to 21 millimeter, which is 66% better than the original one. And you can see the experiment had run in different antenna settings, from 8 up to 64 antennas. And you can see here, this is the original CNN, and beside it are the 3 other architectures that has been used. You can see the error rates, the mean error. And it's very obvious, in all of the results that you will see, that the one when you have more antennas, you have less error, because you have many sources that you can read information from, and you can process the position more accurately. Okay. So this is the experiment for the uniform linear array design, with all the antennas on one side. And you can see as well the same thing. We achieved a 43% enhancement with the original and the mean error. And finally, the distributed array architecture. And this, I think, the best one, and we have achieved, we reached up to 10 millimeter error. So we have dropped down from 55 to 10 millimeter, which is almost 90% enhancement in the mean error. Okay. And after doing this experiment, we thought about if we can optimize on the size of the CNN model, because such kind of models require storage space in the memory and so on. So if we can compress the model by removing the nodes that have less weights or not significant weights, so maybe we can get a smaller size and we not lose that much in terms of accuracy. So we introduced pruning here, and you can see We have done the pruning of the original CNN and on our architectures as well, the same thing. And you can see like the pruned in blue and the unpruned in green. So you can see like the model size. This shows the model size, how it decreased. So you can see like how much we saved in the model size. In terms of accuracy, there is a trade-off. We saw that in some cases the accuracy has dropped to 4% down, if even worse. So this tells us there is a trade-off like between like the size of the CNN model and the accuracy that you'd like to get. So you have to select it, tune it according to the applications that you are trying to deal with. Okay. So this research work has been done. This is the PhD student first research work. So and after that, now he's working on. This is a summary, and like I think we have completed that. And now we move to another step to accelerate some of the known algorithms in the wireless communication. So the one used in detection of decoding and detection, massive MIMOs. And I don't know if you heard about the zero forcing algorithm. So the zero forcing algorithm is a very famous algorithm they used to like decode the information coming from multiple users. So it's very efficient, powerful to if you have multiple users connected to a certain base station. So using that algorithm, it helps you to separate the information of different users and to retrieve the information from each one. So to achieve higher data rates, so we should as well think about accelerating such kind of algorithms on the wireless communication system. So zero forcing algorithm use like matrix operations, and one of the operations that takes a lot of computational power is the matrix inversion. So there's a lot of matrix inversion happening in that algorithm, and this is considered as a bottleneck of the algorithm itself. So we are trying to find a way to accelerate that matrix inversion. Okay, there are several algorithms are used to do this matrix inversion. One of the famous ones like QRD composition and Cholesky decomposition. The QRD composition is one of the famous ones and very simple in terms of like it doesn't have such complex operations, just matrix multiplication and addition. The Cholesky decomposition is more like accurate, it generates more accurate information and have less elements to compute, but it has lots of dependencies inside the algorithm to do the matrix multiplication. So this is maybe, if you implemented the QRD, you'll find it have more performance compared to the Cholesky, but the Cholesky have more accuracy compared to the QRD. So we decided to select, as a before, like first stage to the Cholesky decomposition and try to find a way to accelerate it, both in terms of like software and as well hardware. We started by software, and we tried to deal with. So just before going to the next slide, this is the channel matrix that we are trying to deal with. This channel matrix contains the information from the users to the base station. So we get it. And from this matrix, we'd like to do some kind of operation to get the actual information that has been sent. So we have a plan to accelerate such kind of algorithm in terms of software and hardware, but we started by the hardware, by the software, sorry. But before implementing the software accelerated one, we thought about we have first to generate or to design a parallel algorithm that's independent from the processing platform first. And then starting from that parallel algorithm, we can try to implement it in different ways. So in case of accelerating using software, we selected GPUs and we implemented it using CUDA language, okay? And we have done that implementation we had 2 master students working on that algorithm to implement that. And eventually got a very promising results. We were able to decrease the latency by factor of 53 compared to the original, to the latest state of the art. And we increased the throughput by a factor of 160 of the algorithm. Okay. So, and the future work was to implement that using hardware, using data flow languages. Why data flow? Because we had a previous research between Halmstad and Lund University, where we try to implement some kind of tools that help us, like if we have a system that is in a data flow model, then we can convert the system into an executable form that can be deployed in different heterogeneous applications. And why data flow? Because data flow is a computational model that helps us to exploit the parallelism in your application or system. So as you can see here, these nodes represent like processes or tasks in the system, and the channels here represent the data communicated between different tasks. So if you are able to represent your system or application that way, it will be easily visually to understand the parallelism in your system and try to use it. And you can implement a system that can benefit from that. Okay. So in the previous project, we have done a compiler, a back-end compiler tool that take that model and translate it maybe to C that can run on many or multi-core platform, or VHDL, so you can implement and test an FPGA. And the language that we have used for writing these data flow models is the CAL actor language. It's CAL actor language. It's a language that has been invented by Edward Lee and the University of Berkeley, California. And the tool that we have working on is called CAL to many, from the name from CAL actor language to many languages or implementations. So we are planning to use such kind of tool in our hardware designs and to use the power of like the data flow to accelerate different systems and applications. Oh, thank you. And so any questions?
We have time for one question. I'll run short. Okay, so do we have any questions from the audience? Anyone? I have a question as well, but you can start.
Yeah, I'd like to know how accurate do you need to be? Like, what are the applications? Because you showed that to increase your accuracy.
Yeah.
But how accurate do you need to be?
I think an application for, let's say, to like dealing with delivery system, like when you use, for example, drones to deliver packages and so on, maybe you would require a very high accuracy. But in some other cases, maybe it's not important to know the exact, like if you have an accuracy of 50 millimeter or like a meter by meter square, I think it's enough if you are trying to target some certain geographical area by some add information. I think this according to the application itself. But we are trying to reach the best that we can.
Yeah.
I have two questions. Actually, they're more like curiosities. The first one is the Calculus tool already available for other researchers?
Yes, these tools are already available online on
Okay.
GitHub. You'll find Cal2Many, and there is another tool as well that we are, it's like the next generation is called Streamblocks, and it's available in GitHub.
Oh, that's
And
awesome.
there's a work that as well we were working with Lund and University EPFL, I think, in Switzerland. So, and it helps when you generate, for example, you can generate C language, and I think as well VHDL that's synthesizable using Vivado tool from Xilinx. So
Okay, that's really interesting. I think we're going to check it out afterwards. And the second question was regarding the CNN design that you used for the lots of sensor data and stuff. I see that you use 2D data, but what's the second dimension? Is like, are they localized in space? The information that goes to the CNN, because I see that you have sensor data, time, domain data.
No,
and
this
they're all displayed in a 2D matrix. I was just wondering, like, what configures this 2D second dimension?
no, the information that we have is just related to position on the 2D space.
So that's the
It doesn't have a
actual,
third dimension.
the
Yeah,
actual spatial position
Yeah.
that you use to
but
distribute them in
sure.
the input to the CNN.
Yeah, yeah.
Okay, that's very interesting as well. And okay, do we have any more questions? I'm not sure if I have much time. I actually have more questions, but I can ask later. Okay. So the final question, because I was really interested in the CNN that you used for solving the problem. Do you guys also measure the complexity of the CNN? Because since you want to use it like in a distributed system, probably eventually it can have, become a problem for latency and other types of important aspects.
We didn't actually target the performance at that moment. We were just concerned by the accuracy. But in the future, we try to do the pruning just to enhance the performance. But this experiment has been done on, I think, on a normal computer. But we are planning in the future to take that model and try to accelerate it to find the right architecture to accelerate such kind of models. But we didn't start it until now. I think it's in the future research.
All right, that's very interesting. Do you have any more questions? Okay, so I would like to thank you once again, Professor. It was very interesting. Thank you, Professor.
In case anyone wants to talk, we will be around
next week as well.
Next week as well. Yeah, we're looking like.
Yeah. And my room is 231. You can tell. Okay, thank you very much.
Como fecharam, o pessoal não levantando, eu vou falar. Que engraçado que o plug não funcionou.
Eu dei aula com ele hoje.
Mas estamos hoje com o